Hey everyone, Kai Rivera here, your peptide pathfinder. If you're tackling any advanced biological research, you absolutely need to understand the bedrock of confident discovery. We're diving deep into protein identification mass spectrometry today, a tool so powerful it can make or break your groundbreaking experiments. Without its insights, your research could easily wander into misleading territory. Stick with me as we excavate the treasures within this crucial technique. Let's dig. This powerful technique precisely discovers proteins in samples. It's like a molecular detective game. Researchers use this process for discovery, biomarker research, and compound quality control validation. Without confident protein identification, experiments can easily lead to misleading results. Accuracy is paramount here. Proteins are too complex to analyze directly. First, we break them into smaller peptide fragments. This digestion usually uses the enzyme trypsin, cutting specifically after lysine and arginine. Once digested, peptides are separated by liquid chromatography, entering the mass spectrometer sequentially. Inside the instrument, peptides are ionized and fragmented. It measures their mass-to-charge ratio. These measurements generate tandem mass spectra, which act like unique fingerprints for each peptide. Next, we perform database searching. Experimental spectra are compared against theoretical protein sequences. Software then assigns scores to possible matches, ranking the most likely peptide identities discovered. A high score doesn't automatically mean a correct match. Samples contain noise and interference. Signal-to-noise ratio is a major factor. A clear signal makes fragment ions easier to interpret. Fragment ion coverage is also critical. Strong matches include continuous fragments along the backbone. Precursor mass accuracy is another key checkpoint. Modern instruments achieve incredible precision. This precision greatly reduces incorrect matches, ensuring high-quality data for your research. Retention time stability adds quality control. Peptides should appear at predictable times reliably. Unexpected retention times can indicate false identifications, highlighting the need for careful review. That was quite the deep dive into the foundational steps of protein identification. But we're just getting warmed up. The journey from raw data to confident discovery involves even more layers of statistical wizardry and bioinformatics brilliance. Ready to uncover the advanced strategies? Before we zoom back in, remember to follow me, Kai Rivera, for more peptide insights, and visit Peptides.today for all your latest research news. You won't want to miss our upcoming peptide deep dives. Let's keep exploring. Large proteomics datasets mean manual inspection is impossible. We rely on statistical validation. The target-decoy strategy is widely used. It builds a combined database of sequences. This database includes real protein sequences and artificial decoy sequences for comparison. Any match to a decoy sequence must be false. This estimates the false discovery rate. Many workflows aim for a 1% FDR, meaning one incorrect identification per 100. Public repositories promote standardized reporting, enhancing transparency in all research efforts. Protein identification analyzes peptides, not whole proteins, creating the inference problem. Some peptides appear in multiple proteins due to shared sequences, making identification tricky. Bioinformatics tools apply parsimony, reporting the smallest set of proteins explaining observations. Results are often grouped into protein groups, rather than single proteins, for clarity. Proteotypic peptides are unique to one protein. Finding them strongly supports confident identification. The two-peptide rule requires at least two distinct peptides per protein for confident results. Post-translational modifications, PTMs, add complexity. Identifying their presence and location is crucial. Localization scores help estimate confidence for PTMs. High-resolution instruments distinguish similar masses. Data quality control is essential, ensuring trustworthy results across all experiments and studies. Mass error distributions should center around 0. Otherwise, instruments may need recalibration. Machine learning now predicts peptide fragmentation and retention time with impressive accuracy. That was an exhilarating journey through protein identification mass spectrometry. This field, blending chemistry, statistics, and bioinformatics, drives confident scientific discovery. Rigorous validation will always be essential. Follow me, Kai Rivera, and Peptides.today for all future peptide insights. Before we sign off, a quick legal disclaimer. This podcast is for informational purposes only and is not medical advice. All compounds discussed are for research use only and not for human consumption. Always consult a licensed healthcare provider for medical needs and treatment.